Hi everyone. Today we will look at Wi-Fi encryption. The encryption techniques are covered in a separate course that we have, 585 and 385. So you can learn the concepts and hands-on from those classes. But for this IASP 560, we will look at the encryptions of streaming data over Wi-Fi or cell signals. So we'll look at only those two cases. All others can be or will be or has been discussed in 585 and 385, and all hands-on and programming is very, very important. I mean, encryption without programming, then it is nothing, right? So it should be coded. But at the same time, if you understand the concept, I mean, algorithm itself, then it may help you to modify or improve encryption techniques. So particularly the cryptography requires mainly two lessons. So a lesson about algorithmic concepts, and another lesson will be implementation. How can you really encrypt and decrypt of the messages that you want to send? And also, because we are concerning cyber defense and also cyber offense, along the way of encryption and decryption of messages, and messages are also propagated and transmitted and received. How can we attack? How can we defend? So those are the things that we need to look at very carefully, right? For computer science, concern is that how can we transmit the data with no modification along the way, plus protection of the data breaches, right? All right. Anyway, so what we will do here is that we're going to review a little bit of the things that we you have known already. There are two types of keys: public key and symmetric keys. Okay. If it is a symmetric keys, then the same keys will be used for both encryption and decryption. Typical algorithm for that is DAS code. So in the next slide, we'll do a little bit of the hands-on. By doing so, I want you to recall your lesson learned from 585. At the same time, public key crypto, then the keys, a public key is created, generated, and from that public key, we can also extract the other pair, because the public key crypto actually consists of public key and private key. So there are always a pair of public and private key. They go together. And this public key crypto is very useful and powerful keys when two parties are communicating and sharing the data, okay, sending and receiving data. So rather than share the keys between two parties, so one side creates a public key, and from there also corresponding private key is generated. And if you want to request it to you other party to send back to you a message which should be encrypted, then you can send that person private key. Okay, then the other side, when he receives the private keys, then he can encrypt it and send the data itself, only data. Then the guy who originally generates a public key can receive it and decrypt it by the public key. Okay, so that type of things is widely used. For example, you have a bank internet banking. Okay, so between you and banker. So banker first, when you log in, then banker send you a private key. Of course, the bank possess the corresponding pair, which is a public key. So public key is held by the bank. So bank send you a private key if you want to, for example, deposit the credit card, deposit the check. Okay, then you need to encrypt it. So you encrypt it by the private key, which you received from the bank. Okay, so encrypt it and send it back to the bank. When that message arrives at bank, then banker decrypt it by the original public key. Okay, along that way, no one can intervene. No one can intercept. Although it can be intercepted, for example, at first, banker send you private key. If a private key is intercepted, there's no big deal, right? There's only private key. You cannot generate public key from private key. So there is just key. So private key can be distributed to many people, all the customers. So you are one of those. So when you send it back to the bank for your important messages, then you can encrypt it and send back to the banker only the message, encrypted message. We call that cipher message. Okay, so cipher message is transmitted to the banker. At the bank side, the banker decrypt the cipher message by using public key. Okay, public key. So public key is secretly stored at the bank. So we'll look at that here also. One of a well-known algorithm for asymmetric key is RSA. Okay, so we'll practice it. Just recall. Okay, algorithm types. There are two types of algorithm: block cipher and stream cipher. Here in wireless communications, cryptography, we will look at stream cipher only. Block cipher, that is more static way, and if you have I'm not going to say much because you already know that, right? So instead, what I'm going to do is that we will practice a little bit of those. Okay, here. So for symmetric key experiments, we'll use a DAS. Okay, we can import DAS and then create an object of a key. There is a DES module has a function called new. Okay, this function takes two parameters. So the second parameter is modes. Okay. For example, ECB modes is electronic code block modes. There are different modes also. For example, cipher block chaining mode and some others. Also propagate something. So one of the simple mode is ECB. And the first parameter for this key generator is to take the seed text. Okay, so it could be a number. Actually, it is 8-byte size text. Okay, you can do either this, or you can make, for example, Mercy, MERCY. Mercy is 5 characters, right? And then 3 more. So Mercy 1, 2, 3, maybe, or 1, 2, 3 Mercy, or 1 MER, 2 CY, 3, whatever. Okay. So once you have the key, then you can encrypt and decrypt. All right. So we'll practice that. For asymmetric cryptography, we are going to use RSA algorithm. This is a well-known algorithm, right? Initials of 3 inventors. Okay. I think 2 of them were in MIT, right? I think one of these 3, I think now only one guy in MIT. Okay, anyway, so you need to import RSA from the package crypto.public key. Okay. I wanted to use Anaconda Python rather than native Python, because Anaconda has already this software packages in it. Otherwise, you have to install it. And then you can use a random number. So random number can be generated in this way, random.new, and then there is attribute read, and then there is a random number. So with that random number which is generated, and then we can also decide the size of the key. So 1024 byte key. This usually in RSA someone may ask, can I make this smaller than this? No, it should be at least 1024. Okay, right now the current version of RSA. Can we increase? Of course you can increase. As you increase the size, you can increase by multiple of 256. So multiple of 256 and over 1024. That is the size of this. Then you can generate the key. Okay, so from this key dot public key, for example, then this RSA is a little different. The way that I explained the earlier asymmetric, you can simply switch private key and public key like this here. Okay, so from this key in this case is a private key. So this private key is held by a banker, and then generate a public key. Okay, so public key is distributed to the bank clients. So when you receive this public key, and this makes more sense, right? It's a publicly distributed. So when you receive this public key, you can encrypt it and then send it back to the banker. The banker decrypt it by the key only. So the key here is nothing but private key. From this private key, you can generate public key. So both are paired. Okay. In principle, it doesn't really matter. If you have one pair to encrypt, then you can do decrypt by using the other pair, right? That sounds perfect. That's what we are trying to do. All right, to do that, let's practice in Paizo. So I can bring the Paizo here. Let me see. Okay. So as we did, for example, from crypto.cipher and then import dash, okay, and then dash.new, I put there, for example, see here, first one is a key. So mercy that the key that you might know, that should be 8 bytes. So 2, 4, 6, 8 byte. And then second one is the mode. So dash dot mode ECB. Okay. And I'm going to store that in, say, dash, or yeah, dash. All right, and then I can say message equals hello, kill it. Secret message. Okay. and then I want to encrypt it. Encrypt that message, and I want to save this to cipher. Okay, so I encrypt it. Oops. Input string must be multiple of 8. Multiple of 8. Oh, so message should be multiple of 8 also, because this 8 bytes multiple used, like block by block by block by. So what we will do here is hello 245, hello 245, hello 6 7 8 1 2 3 4 5 6 7 8. All right, so that I can do this. Okay, so it works, right? Because this is a multiple of 8. So this the key will be used 2 times. So hello kill it is, if we look at that, then that is the thing, right? This is a byte code B, and this is it. That is sent out. If you want to decrypt it, you can decrypt and then cipher. You can decrypt and cipher, and then I want to say origin. Okay. So what is origin? Hello kill it, right? So this was encrypted this when I decrypted that cipher, and it came back. Okay, so it works that way. Sounds good, right? This is a dash code. Dash code has a lot of issues, right? As you could see, this is a block based algorithm, so that the text should be, the encrypted text should be multiple of 8 in this case. What else can I say? I think that is it. Right. All right. Let's do now then RSA, so asymmetric keys. In order to do that, from crypto.cipher and import RSA. Okay, I think it should be a public, not cipher, or public. Okay, public, and enter. All right, and then from crypto import random. So we want to use a random number generator, right? Rand equals random.new.read, and I have a rand, and then RSA dot, we have a generate. So we have a generate that takes 1024. That's the size of that, and then the random number is used, and this will be a key. Okay, so key is generated. Fine. So if you type key, then that is the key. But from this key, you can generate a public key. So pub key equals key dot public. Okay, see a public key. That's a function. Then pk is this. In order to that pk, you need to do here export key. If you do that, then this is the public key. Okay, from here, this is a public key. Okay, so public key is generated from private key. Key is the private key. Okay, so for example, if you do k dot export key, then you can see the private key here, open and close parenthesis. This is a private key. Okay, so this private key is held by the bank, and then the corresponding public key will be sent to bank clients. So bank clients, whatever the message that bank client wants to send, that is encrypted by this public key. Okay, pub key and the key, two things. So what we need to do is that say message equals, and then we can say hello, please sign on this application. Okay, so that is my message, but I want to send it using a public key, right? So public key is publicly distributed to the client. So pub k dot and encrypt and the message. So we want to encrypt that to so 32. As you can see, there is an error. The error is that object has no encrypt attributes. Ooh. Let's say pub k encrypt. Message. Do it again. Pub k. This is pub k, right? Pub k that we have, and then dot. Then we can do encrypt. This is encrypt, and then message. Okay, so this works, but the only problem now here is that unsupported operand types. See, if you hear this guy goes back to Anaconda library site package cryptor, and there is a public key RSA and public key PIRSA. So to solve this, you need to encode encode this UTF-8. So UTF-8, this is a code. Okay, so message itself needs to be encoded. It's not encrypt, right? Encoded into the certain type. Here is a type error. Then it can be encrypted. So the message that you want to send here, hello, please sign on this application, is encrypted in this way. Okay. So what I'm going to do is that I'm going to save this to, for example, cipher. Okay. So cipher is nothing but that. So this cipher, this message is transmitted to the bank. So along the communication channel, so no hackers can compromise this data. Message cannot be compromised. Okay. Once it is compromised, still the hacker does not have a private key. It cannot be decrypted. So this is just code. They don't understand what it is. So, but however, the banker, when this message is received, then banker knows how to decrypt it, because the banker has a private key. Private key is, in this case, just key. And then we can do encrypt, decrypt. Here, decrypt. Okay, this function decrypted for cipher. Again, this should be encoded. If you do this as is, then you probably have the same problem. Oh, no, we got it, right? Hello, please sign on this application. So perfect. So you simply do that. Only the encrypt algorithm does not take the text only. Okay, yeah, this is not text, therefore it can be decrypted it. So the banker successfully understands what the client wants to do. All right. So this is the little bit of a review for the DAS code and RSA asymmetric algorithm. And however, over the Wi-Fi communication, data will be a streaming data. So we cannot encrypt them block by block as we did for RSA and DAS code, right? So more like the situation is in this case. Symmetric key, right? Internal state is updated every after block. Symmetric key cipher may be good. Why? Because asymmetric, like a public and private key, they needs to generate and share. But for Wi-Fi signals, they don't share, right? Keep sending wherever you go. It's not server and client fashion. So key should be shared. It's not pairwise asymmetric key. And also state-driven, which means it operates on arbitrary message length. So length is not really restricted. So the algorithms that widely used is RC4. That is used over SSL and WEP. WEP is one of and very old Wi-Fi encryption technique, and SSL is still used for example, secure shell, okay, for the Linux administrator. And another thing is A5/1, which will be discussed in cell phone signals. That is for GSM mode. So we'll look at this when it comes to that cell communication. For streaming cipher, also some of you may know from IASP 585 or CISC 385. So I'm going to give you a short the exercise here, and then this is a real exercise for RC. RC is the algorithm that we want to learn. So RC or ARC, learn for this module. The real algorithmic concepts will be discussed later in this module, as you could see here. So encryption algorithms, there's a lot of algebraic computation is involved. So we will look at this maybe next week, not this week, okay? But instead, I'll give you quick motivation and quick implementation, okay, which is RC4. So for this, you need to import crypto cipher from that packages ARC4, and key is generated multiple times, okay? So ARC4.new, whatever the seed text that you want to use can be shared, okay? As far as you use that ones, if you use it differently, then you cannot get the decrypt. So for example, key 1 and key 2 separately generated, as far as they have the same seed key. In this case, they are not, right? But if they use the same one, for example, CTX, then although they don't agree, although they are not in one device, for example, this one had this the key is held in Wi-Fi router, and another one is in your laptop. So your laptop needs to communicate to your Wi-Fi router. All encrypted. How can they understand between them? So that is in this way, okay? So I'll give you also a short demo for that. Then you will know very quickly how it works. For that, you need to also import from crypto.cipher, import, and ARC4. See here, ARC4. Okay, so we import that, and then let's say between you and Wi-Fi, the same key is shared. For example, let's say CT equals 0, 1, 2, 3, 4, 5, 6, 7. Okay, so key, so Wi-Fi key equals lc4 dot, and we have a new nct, and then my k equals alc4 dot new city. Okay, so now Wi-Fi K is encrypted. The message is let's make a message first. Okay, so message equals between you and Wi-Fi. Okay, so you can say kill him, and then let's say Wi-Fi K encrypt. Encrypt message, and then you can say message, let's say cipher. So it is cipher. That is a message. That message is encrypted at the Wi-Fi router, and that is sent to me. Okay, so when I receive it, I need to decrypt it, right? So what they share is a CT only, right? As far as they share this, then simply it generates, and then we don't do anything between Wi-Fi and myself. Wi-Fi, what Wi-Fi can do is to encrypt or decrypt. Likewise, me decrypt or encrypt. So I will do decrypt here. My k dot, and then I will do decrypt. Decrypt what? The one that you received, which is a cipher, right? When I do that, it says this same message. Okay. So this is streaming encryption, RC4, and the one that we looked at, we didn't look at the package inside. We simply use it. Okay. So for the rest of this module, what we will do is that we will look at the concept, algorithmic concept behind that application. All right. So until the next week, I want you to read the rest of this. So those who understand mathematical computation, please practice and get some idea. All right. For someone, this algebraic computation may be uneasy, but hopefully most of you can understand this very easily. All right. Okay. I'll see you next week.